Okay, I think that we all had a pretty great time talking about angular position, but now we're going to step it up a little bit and talk about velocity. So, linear velocity just tells us, if we recap here, linear velocity on average is the change in the linear position divided by time. It turns out that angular velocity is exactly the same idea. It's telling us how rapidly the angular position is changing. So linear velocity, how rapidly is the linear position changing? Angular velocity, as a result, is how rapidly is the angular velocity changing. So it looks something like this. And this does give rise to the idea that if we want to look at what is the variable for it, and I'll try to make it, that's not too bad, something like that. This is in radians per second, and this symbol here is called omega. It's not a W. Many of you are going to try to rattle me by talking about it as being a W, but it's not a W. It is a Greek symbol, just like theta. It just happens to look a lot like a W, but it starts with an O, so it clearly cannot be the same thing. So we have omega. This is a lowercase omega. We'll play more with the capital omega when we get to circuits. But that's really all that there is to angular velocity. Its direction is exactly the same as the direction of the change in the angular position. And so if you look at these first two here, where theta is approximately the same, that means that we have approximately the same angular velocity during those segments because it covers the same distance in about the same amount of time. If you look at this segment right here, it's covering a greater angular position in, let's say, the same amount of time, and so it must be going faster, and this one even faster still. That's the basic idea. The direction is the same as whatever this is, so this would still be into the screen. Now, how do we convert linear to angular? Well, we operate under the same principle, and if I just take my conversion, which I have over here, which is just the definition of what is a radian. So if I have x equals theta times r, if I just divide both sides by t, right? So if I'm dividing my x by t, and I'm dividing theta by t, then I get v equals omega times r. So that is our conversion. So we have v equals omega times r. Now, one thing that I've left out here, because it's unpleasant to really talk about, is that these things right here, these are actually cross products. We're going to talk about cross products more when I'm in class, but for now, just be aware that there is something called a cross product. You probably should have learned about it already in math class. If you haven't, then I'll have some teaching to do. But otherwise, it's a cross product. We're not going to worry about it right now. So that's all that's involved with angular velocity. Hopefully that makes sense. The harder one to deal with is acceleration. And the reason why it's a little bit harder to deal with is because there are actually two types of acceleration. There's an acceleration called tangential acceleration, as in tangent to a circle. And there's also another type of acceleration called centripetal or radial. And I'll just use an R here. But you might also see this as a C, right? So the centripetal acceleration or the radial acceleration. Now, I'm going to focus primarily on the tangential acceleration, but I will talk about this briefly. In terms of tangential acceleration, that has to do with how rapidly we're talking about something changing its linear speed. So if I'm looking at a point on the edge, here it's moving at a certain speed, here it's moving at basically the same speed. So there would be zero tangential acceleration here because this point is moving at the same speed regardless of where we're located. But if I get to here, well, it might still be traveling at about the same speed. Okay. One thing that we're looking at here, though, is that the speed is the same, but the direction is changing. So we know that there's a centripetal acceleration, right? There's something that's drawing it in towards the center of the circle to change the direction. So no matter what happens, we will have radial acceleration as long as the direction of motion is changing, as long as it's doing something vaguely circular. It doesn't have to be speeding up, it doesn't have to be slowing down in order for this to occur. However, for the linear speed to be changing, we would need some sort of tangential acceleration, and we start to see that when we get over into this range. So here, it is now traveling considerably faster than it was over here, and over here it's traveling even faster. So clearly we're speeding up. The symbol that we use for tangential acceleration's counterpart, the angular acceleration, is this. Some people say it looks sort of like a fish. It's, once again, not a fish. It is a Greek symbol called alpha, and the units for it are radians per second. And so if we just go back and look at this, here we have zero angular acceleration. Why? Because it's going through the same angles in the same amount of time. So the angular speed is not changing. But if we look over here, we've now covered a greater angle and yet a greater angle, and so our angular speed is changing, which means that there must be some sort of an angular acceleration. And the equation for this is like so. We would have angular acceleration, on average, is equal to the change in the angular velocity divided by the change in time. So one thing that you'll notice is that they're all analogous, right? So for linear velocity, we had x over time. For angular velocity, we had theta over time. X and theta fulfill the same role. They tell us linear position, angular position. V tells us linear velocity. Omega tells us angular velocity. To find linear acceleration, we would do delta v over delta t. Angular acceleration, we do delta omega over delta t. And the conversion between them, once again, we just do the same thing. We divide everything by time. So divide this by time, divide this by time, and ultimately we get this, which is A tangential equals alpha times r. Okay, and this is meters per second squared. This is meters and radians per second squared. So if we take radians per second squared, multiply by meters, something better has come along, and so we end up with meters per second squared. So that's the basic idea behind all of these different things. Now just briefly, the angular acceleration, there's no analog for this radial or centripetal acceleration with angular acceleration. They're not necessary to go together. So for example, in this first part here, there was zero angular acceleration. This doesn't care about angular acceleration. If it's going in a circle, then it cares. And so what we actually have, if we want to deal with conversion, is we know that the equation for centripetal or radial acceleration is v squared over r. And I know that v equals omega times r, so I can write it out like this, where I have omega squared times r squared over r, which just ends up meaning that we have the centripetal or radial acceleration is equal to omega squared times r. And this highlights once again that we care not about whether it's speeding up or slowing down, but whether or not it's going in a circle. So if it has an angular speed, it's going in a circle. And so this cares about, does it have some sort of an angular speed? If it does, then we're going to have centripetal acceleration. The larger the angular speed, the larger the centripetal acceleration. The further away the point that we're interested in is from the axis of rotation, the more radial acceleration we're going to have. So this is the basic rundown of your x, v, and tangential acceleration, and how they relate to angular position, angular velocity, angular acceleration, how you can convert between them, and just a quick touch on radial or centripetal acceleration and its relation to not angular acceleration but angular velocity. Now I know that there's a lot of terms that sound very similar here, and so this is one place where you're going to have to go and you're going to have to study up and learn what these terms mean so that you don't get them confused. In the next video, what I'm going to do is walk you through how to deal with kinematics with this, or kinematics types of problems, and do an example with you.